Hi everybody, welcome to chapter 2. Again, we are starting in this one at chapter 2.3, which is atomic structure and symbols. Hopefully we'll run through the biggest topics of this chapter as well to help you along the way. So, first off that we want to get through here is starting with the location of our subatomic particles. All right, so atoms themselves are made up of protons, neutrons, and electrons. All right, and so the nucleus houses the protons and neutrons, and that is also where most of the mass is located. And then the electrons are outside of that, and they're really, really tiny in comparison to the protons and neutrons. So the nucleus is really tiny itself, right? It's about 100,000 times smaller than the size of an atom is. And an atom is already comically tiny. Okay? So let's think about that though. Like I'm going to kind of bring it up to something where we can kind of blow that up into like a bigger ideal. If we took a nucleus of an atom, right, which is really, really small, but if we took that and made it the size of a golf ball, right, so we have the nucleus is the size of a golf ball, then the diameter of the entire atom would be about 2 miles, all right? Or the radius out from one side to the other would be about a mile away, right? So that's how big the atom is in comparison to that nucleus, right? Think golf ball versus like a 2-mile diameter all the way around it, right? So those electrons are flying around in like all of this really pretty much empty space, and the protons and neutrons are crashed into this little tiny area there in the nucleus. All right, so next up we want to talk about like some properties of our subatomic particles, and I would know this slide or be able to come back to it as you're going to have open resources and stuff like that for taking your exams and stuff. But notice that when we talk about protons, we're going to give them the symbol of a P with a little plus sign there. That's because we usually talk about protons as being positively charged, right? Every proton has the exact same charge, and it's always a charge of +1. Right? So we could put a little plus there as well instead of just the 1, but they're always positively 1 charged. Neutrons we show as like the symbol of an N with a little not symbol or a 0 up there. That's reminding us that the charge of a neutron is neutral, has no charge whatsoever. And then electrons are an E with a little minus sign up there. That means our electrons are -1 in their charge. Protons and electrons have exactly the opposite charge of each other. So if you've got a proton and you've got an electron, right, if you've got one positive thing and one negative thing, they're going to cancel each other out so that you've got an overall charge of 0. Right, some other information on here, right, is we've got the mass of things in atomic mass units, and when we generally talk about them, what we really are going to care about for everything in Chem 1 is that the mass of protons and neutrons are basically 1, and that the mass of an electron is basically 0. Right? Also out there we've got that the mass in kilograms of these things, and that's just to show that our electrons, like they do have a mass even though we call that mass 0, right? But that mass is really, really tiny in comparison to the mass of our protons and neutrons, right? It has a mass out there of times 10 to the minus 31st versus the protons and neutrons, which are times 10 to the minus 27th. They're all really, really tiny numbers, right? But times 10 to the minus 31st, right, is about 1,000 times smaller than those of our protons and neutrons. All right, so let's talk about a few different things that when we want to describe our elements along the way, how we can describe them in shorthanded notation so that it's easy for us to kind of like convey all the information that we need. All right, so number one is that we're going to bring up things that are called atomic numbers and mass numbers. All right, the atomic number is the number of protons that are in the nucleus of an atom. Okay, now this is what defines our element itself. All right, and this number is always located above the elemental symbol on the periodic table. Okay, so when we look at our periodic table, which we're going to do soon, right? But when we look at our periodic table, there's going to be a number above the elemental symbol, and that is the number of protons. That is also called our atomic number, and it's given the symbol of Z to things. All right, then, right, we can also have what we call a mass number. That's given the symbol of an A. The mass number is the number of protons plus the number of neutrons. All right, now, this is different than the actual mass of what an element weighs. The mass number is just the number of protons and neutrons. So this will be right, this is going to be a whole number. All right, when we talk about the mass of things, they're going to have like, you know, the mass of hydrogen, or let's say the mass of, let's say nitrogen, right, is 14.014. Okay, that's the mass of nitrogen. But the mass number of nitrogen is going to be like 14. It's not going to have any decimal places because it's got to be a whole number, because the exact number we're counting, if we remember back to like chapter 1, we can count the number of protons and we can count the number of neutrons and add them together. All right, if we want to calculate the number of neutrons from these values, you can do the mass number, right, which is protons plus neutrons, and we subtract off the number of protons. That would give us the neutrons. So A minus Z would give us the number of neutrons there. All right, our chemical symbols. Our chemical symbols are abbreviations that will tell us something about our element. They define our element by, you know, like some sort of a 1 or 2 letter symbol. The first letter is always capitalized. Don't write it as a lowercase letter. And the second letter, if there is one, is always lowercase. Don't put it as being capitalized, or else those are incorrect. Okay, here's what the symbols are based on their elemental names. A lot of these are super easy for us to figure out, right? Hydrogen. Right? Hydrogen is given the symbol of H, right? Makes sense. It's based off of its name. Helium. Right, well, H was already used. Right, so helium is He. It's an uppercase H, it's a lowercase e. Right? Then there's other ones that don't look like they make as much sense to us. Right, like tungsten is given the symbol of W, but its German name is Wolfram. All right, and so that's where the symbol of that comes from. So they're always based kind of off of their names one way or another, but it doesn't necessarily mean that those are based off of their English names, right? So we have to kind of get that, right? But again, right, you're not going to have to like memorize, you know, like all 118 elements that are out there or anything like that, right? But some of them you're just going to kind of get used to seeing enough during the semester that you're going to be like, oh, I know oxygen is O, right? You might even, by the end of it, know that iron is Fe or something, you know, some of the tougher ones. But, you know, again, there's a reason you have a periodic table, right? Is that it's not like you're going to be out there in the real world and be like, I don't have I got to know what iron is, but I don't know what it is. You will be able to have resources to look things up. All right. Now, most of the time our atoms are going to be in their neutral state, meaning that they have the same number of protons and electrons, right? And so they would have no charge associated with them. All right, so if you just come across like a random carbon, it's probably not going to have a charge associated with it, right? Or came across a random sodium atom, it's going to be like, hey, it's neutral, it's not going to have a charge. It's going to have the same number of protons and neutrons. All right, but sometimes our atoms like to gain or lose electrons. And when they gain electrons, right, we're going to say that they're called anions, okay? Because when they gain more negatively charged things, they themselves become negatively charged. They can't change the number of positive things. There's the number of protons. That describes what the element is. The number of protons can't change, but the number of electrons can. When we lose electrons, they become what we call cations, right? They are negatively charged species. Or sorry, they are positively charged species because they have lost negatively charged things. So they have fewer negatively charged things than they used to. All right. Metals usually like to lose electrons to become cations, and non-metals like to gain to become anions. So you could have something like sodium, all right, which sodium, when it's neutral, has 11 protons and 11 electrons. All right, sodium is a metal. All right, and again, right, metals tend to lose electrons. So sodium with a cation, right, could lose an electron, right? So it went from 11 electrons to 10 electrons there. Can't change the number of protons or else it wouldn't be a sodium anymore, right? But notice that when I went from 11 positive and 11 negative things, it was 0. They would be neutral. When we've got 11 positive things and 10 negative things, 11 minus 10, right? We have a plus 1 there. Right, that's where that value came from. Right, and our nonmetals like to, kind of do the opposite. Our nonmetals like to gain electrons and they become negatively charged. Again, we're going to go through these a lot more as we kind of hit future chapters as well. Right, we can also take our elements and we can form things that we call isotopes. Right. Isotopes are elements with the same number of protons, but they have a different number of neutrons. Okay, so here we're not changing our number of electrons. We can't change our number of protons or else we would change the element itself. So here we're changing the number of neutrons. Okay, so when we have these, right, there are, say, two naturally occurring forms of carbon. All right, so we can have what we call, all right, so carbon has 6 protons, has to. All right, so this can either be carbon 12. Okay, that's one way we write it, is with like the C-12 there. Okay, that has 6 protons and 6 neutrons, right? The mass number is 6 plus 6. That's what we're writing down here with our isotopes. Or I could have carbon 14. It has 6 protons. All right, and so the number of neutrons for carbon 14, well, 6 plus what gives us 14? It has 8 neutrons. Okay, so one way we can write these as C-12 or C-14. All right, another way that we can write these is we can write down what the mass number is as a superscript. So we could see this as carbon 12 like this and carbon 14 like this. And even further, another way that people write this is sometimes, okay, we write the mass number as a superscript, right? We can write down the atomic number as a subscript beforehand, like that. So we might see the symbol for carbon 12 and carbon 14 like these guys here. They all mean the exact same. All right, now it's just how much information is being presented to us. Like the carbons with the 6s there, that reminds us that there's 6 protons. But, you know, we can always look at the periodic table to remind ourselves that there's 6 protons if we needed to. All right, now, next thing that we're going to do is we're going to calculate the atomic masses of things. Okay, the atomic masses that we're going to find is that these are different than the mass numbers. These are very specific masses. And so these are going to be a weighted average of all of the different isotopes that are present out there. Okay, now notice that it says that it's approximately equal to the mass number. Okay, but it's not going to be exactly what that is. Okay, because neutrons and protons don't exactly weigh 1. Yeah, we say that they weigh about 1, and for our stuff we usually are just going to kind of round to 1. But if we look back at that thing on like slide number 3 there, right, the mass of a proton is actually 1.0073, and the mass of a neutron is 1.0087. So they're not exactly 1, so they're approximately that amount. Okay, now if we want to find the actual atomic mass of things, then we have to find a weighted average. Okay, we're going to do that as a sample problem on our next slide here. So this is the neon is 91.84%, all right, neon 20, and we give the mass of neon 20 there. Notice that like the mass of neon 20 is not exactly 20, it's 19.9924. And we've got 0.47% neon 21, and we've got its mass as well. All right, so when we want to do this, oh, we also have a neon 22, which is 7.69%, and we've got a mass there. Okay, in order for us to solve these, okay, what we're going to do is we are going to take the sum. Right, that's what our little sigma means, right? That means that we're going to take the sum of what follows it. All right, so we're going to take the sum of the fractional abundance. Okay, the fractional abundance, right, is a fancy term for us saying that we're going to take the percent and divide by 100. All right. Times the mass. Okay, so what we're going to do then is we're going to start with neon 20. Its fractional abundance is, all right, 91.84 divided by 100 is 0.9184. Right, and we're going to multiply it by its mass, 19.9924 AMUs. All right, we're taking the sum of, so we're going to add to that. All right. Well, we've got our 0.47% of our neon 21. Well, 0.47 divided by 100 is 0.0047 times 20.9940 AMU. And then we're going to add to that one as well. All right, 0.0769 for our neon 22, and its mass is 21.9914. Okay, so we get this to be then 20.15 AMU. Right? That's how we're going to calculate the weighted average of something, right? Doing that sum of the fractional abundances times each one of their masses. All right, let's move on to, right, 2.5, the periodic table. This was pretty short. I just want to bring up here right? By looking at the periodic table, right, there's a lot of information that can be gleaned from the periodic table, right? Remember, I told you that the atomic number would always be above the elemental symbol, right? That's that number of protons there. The symbol, right, is usually going to be written there right smack dab in the middle. It's going to be that 1 or 2 letters that's telling us what the element is. The atomic mass. Right? That is that weighted average that we just found. Right? Because whenever you get, say, some neons that are out there, right? And if we look, remember that we just solved for neon being 20.15, and it's really hard to see, but our neon out here is basically that. I think it says 20.16 on this one, but it's pretty darn close. There's probably a rounding issue of why we're off by 0.01, but you know what? We pretty much got it, right? The reason that's that is because those are just like, whenever we have neons, like it's not like you're going and grabbing like a single neon. You're going to go and put together a whole bunch of neons, right? And so the neons that you have are going to have some sort of a weighted average. That's why we report those atomic masses as their weighted averages there. Right? And we also notice from our periodic table, there's some other things. We're going to go over the periodic table a lot, but right down there in the right where my head is, right, like all the ones that are in yellow, right, they are metals. Right? All the ones in green are non-metals, right? So, and then the ones that are in this little pink range that are right in between are metals and are non-metals there, right? Those guys are usually called metalloids. All right, so they kind of have properties of both being metals and they have properties of being non-metals. There's some other things that we're going to discuss along the way, like down here there are things that are called lanthanides and actinides. All right, we're going to bring up like the different parts of our periodic table way more in depth in a future chapter to come pretty darn soon. There's also things that you can probably get off of the periodic table depending on which ones you've got. Like in this case, this also shows us ones that are solids at room temperature. The ones that are solids at room temperature, the atomic symbol is in black. If they're gases at room temperature, the symbols are in red. And the couple of them that are liquids at room temperature, bromine and mercury. Mercury is Hg, by the way, there. It's kind of an oddball one to spot whenever you're trying to get its name. They're in blue on our periodic table. So there's some other things that you can get depending on the periodic tables that you're given. All right, now let's move on to section 2.6. which is molecular and ionic compounds. Now, again, there is an entire chapter devoted to molecular and ionic compounds to come. So this is just kind of us dipping our toe in the pool to kind of get, an idea of what we're talking about with those things. But molecular compounds are when we have 2 or more nonmetals that come together. Okay, so molecular compounds are things like water, H2O, right? Hydrogen's a nonmetal. Oxygen is a nonmetal, right? Carbon dioxide. Carbon is a nonmetal. Oxygen's a nonmetal. No, right? It's a molecular compound. Then there's things that are like what we call ionic compounds. Those are made up of cations and anions. What we're really talking about for the most part is when we have a metal and a nonmetal come together. All right, sodium chloride. Right, table salt, we probably have heard of this as being before, right? Table salt is a good example of an ionic compound. It's a metal and a non-metal coming together. All right, molecular compounds, right? They exist because they share electrons whenever they bond with each other. All right, so it's like, they want to like kind of like say like, hey, I want to have like, joint custody of the kids where, they're going to share part of the time the electrons are going to be around one of the elements, part of the time they're going to be around the other one. Right? Molecular compounds exist as discrete molecules, all right? So they're individualized molecules that aren't really associated with each other. They can be close to each other and have these things that are called intermolecular forces that we'll talk about, of why they kind of stick together, but they're really all on their own. Right? And again, I gave some examples on the previous slide, things like water and carbon dioxide, but there's also sugar there, C12H22O11. Right? There's plenty of examples out there. Right? But molecular compounds made up of nonmetals. Right? Ionic compounds, right? Again, we've got a little reason thing. Ionic compounds come from the transfer of electrons from one species to another. So they're not sharing custody of the electrons. One species is like, hey, you can just completely take this electron from me. So we've got our sodium chloride, right? And so if you remember back, like I said, right, sodium doesn't mind becoming like a sodium cation. So what sodium cation really is, what this compound really is like a sodium cation with a chloride anion. So what we've done here is the sodium, right, has given away an electron, and the chlorine has accepted that electron, and it's around that chlorine all the time. So the sodium is now positive because it got rid of something negative, and the chlorine is negative because it now has an extra negative thing around it all the time. Right? Ionic compounds, it says, exist as large crystalline structures. Okay, so what I'm saying by that is like, you don't find like one specific sodium chloride. What you find, like if you ever look, right, at salt, if you really get up and look at salt, right, it looks like a little crystal there. Right, because what it really is it is like a three-dimensional crystal of those ions going back and forth and back and forth and back and forth. All right, now, again, a lot of times this can be just a metal and a non-metal, but it doesn't have to be. It can be something like this NaHCO, which is, this is a cation with an anion here. What this really is this is sodium and that HCO3 has been the thing that took that electron on there, right? Or out there, sodium, then it doesn't have to be sodium, we just have a lot of examples of sodium here, apparently. With that hydroxide, that whole hydroxide has become an anion and accepted that electron. Okay, we can use the periodic table to predict ionic compounds. Okay, so notice that, right, things in group 1 love to become +1. Things in group 2 love to become +2. All right, if we go away, so let's go away from our noble gases out here, is out there in group 18. Right, our noble gases, if I work away from there, right, notice that these like to become -1. And then if I move over another one, they like to become -2. And then they like to become -3. Right, there's some other ones that are out there. Notice that the transition metals, a lot of them have varying charges. And so they're really hard to figure out exactly what they can be because they have what we're going to call like varying oxidation numbers out there. They don't always like to lose a certain number of electrons. Sometimes they like to lose a certain number. Sometimes they like to lose a different number of electrons. Zinc always loses 2 electrons to become zinc 2. And silver always loses 1 electron to become +1. those are probably the only two out there in those transition metals that I would know. Right? Don't focus on any of the other transition metals too much. But know those main group elements, which are the ones that I kind of pointed out there, those group 1 and 2 being +1 and +2, and then group 17 love to be -1, group 16 loves to be -2, and group 15 loves to be -3 there. Those ones, that's going to be really helpful to us later on. So, like as you are preparing for study guides or something for an exam, you might like print off a periodic table. You might want to write those sorts of things down so that they're really easy to kind of like look up without having to like, jog your memory on it or memorize or anything like that. All right, that concludes chapter 2. So see you when we get to chapter 3.